My name is Steve Zdanswyk. I'm a professor from the University of Pennsylvania, and I'm going to be telling you today a little bit about a project we've been working on for the last many years called Vellum, which is about verifying the LLVM. And before I get too far, I want to emphasize that this is a big collaboration with many students and postdocs and collaborators over the years. And I wouldn't be able to be here to tell you about it without all of these great people. So I wanted to thank them. So what I'm going to tell you about today is our ongoing work to do formal verification of LLVM code. Just by a show of hands, how many people here are familiar with LLVM to some extent? Okay, most people. Okay, that's actually more than I expected. So I'm going to start with a little bit of a review of LLVM, just to get us all on the same page, and then talk at a fairly high level about how we define a formal semantics for it in the interactive theorem prover Coq, and kind of sketch how we use that to do some interesting things like verify program transformations and wind up with some future and related work. Okay, so let's jump right in. So for this audience, it sounds like most of you are familiar with the LLVM compiler infrastructure. So it's this great compilation framework that was introduced by Chris Lattner a while back. And the basic idea is that the LLVM, which the low-level virtual machine, provides a sort of common intermediate representation for compiling many, many source languages to many different target platforms. So the idea is it provides a kind of common abstraction that you can use to lower C or C++ or Swift or Haskell or Scala, et cetera, to your favorite architecture. And for the purposes of this talk, the most important pieces of the LLVM are its intermediate representation, this so-called IR. I'll say a little bit more about what that is in a minute. And the nice thing about the LLVM as a compiler infrastructure is that it's structured as a kind of series of analyses and transformation passes that work in terms of this IR. So that means that if we study this intermediate representation or understand its properties, we can sort of reuse that insight throughout all of the compiler. And of course, this is not to say that there isn't lots of interesting work going on in the front ends that lower the code to the IR, or in the back ends, which do high-performance code generation for various architectures. But for the purposes of this work, we've been focusing on this middle piece. So just as a refresher, and for those of you who haven't seen it before, I'll just give a quick overview of what an example LLVM IR program looks like. So here to the left of the screen, you'll see some sample LLVM code. This is my favorite, everybody's favorite factorial function. You can write it in many different ways. This one happens to use a kind of loop structure. And I don't want you to read all of the details of this code, but just get a sense of what its structure is. So this is defining a top-level function called factorial. It takes a single 64-bit integer parameter n, and then it has a bunch of blocks, basic blocks. So the LLVM IR code is structured in terms of the classic control flow graphs that we're all familiar with from a compiler's class if you've taken one. And so each block in this control flow graph has a label. The labels, or the blocks themselves, contain essentially straight line code for writing down operations like arithmetic and bit shifts and comparisons and loads and stores from memory and so on. And then the blocks are wired together by essentially gotos or conditional branches that turn these blocks of code into a control flow graph. One interesting design choice that LLVM makes, and is also well appreciated in the compiler literature, is that it uses what's called static single assignment, so SSA, which means that if you look at each of these instructions, essentially you can think of them as an assignment to either a local variable or a register, something like this. But that assignment only appears once. So once you've introduced such a definition, for example, %n1 gets some value, you'll never overwrite that value. And so in some ways, this makes the LLVM IR code a bit more like a functional program where you can think of these as let introductions as opposed to just sort of C-style imperative updates. And that's a nice representation choice for doing various kinds of analyses and optimizations in the IR. As a consequence of doing SSA, one of these sort of maybe unfamiliar things that you will see in LLVM code, if you're used to programming at the source level, is what are called phi nodes. And these are sort of fictional instructions that semantically essentially assign their left-hand side based on the dynamic behavior of the program. So the intuition is that you have a bunch of branches, and if, for example, the code jumps to the start block via the then block, then the phi node will select out in this case, n2 as the value that will be assigned to n1. And if you happen to come in from this entry block, which is implicitly named 0, then you'll get the value n. So phi nodes sort of semantically, dynamically choose based on where the code came from, and that's useful for maintaining this SSA invariant. The other interesting thing about LLVM IR is that it's typed, so you'll see all these little I64 and I64 star annotations sprinkled throughout the code, and that's just LLVM's notation for 64-bit integers and pointers to 64-bit values. It has a rather rich type system that I'll talk about in a minute. So that's just kind of a top-level tour of what LLVM code looks like. But if you dig a bit deeper, as I said, LLVM supports many other features. So it has essentially a C-style type system. So you can define structs, arrays, integers of varying bit widths. There's not really any constraint on the size. You could have a 17-bit integer if you decide to. Pointers, vectors, and so on. The type system is a bit like C. So LLVM was originally intended as a C intermediate language. And so it sort of inherits a lot of the features from C. So its structs are more there to define layout, padding, and alignment in memory than sort of high-level abstractions. And it has many other features that it's acquired over the years. For example, you have primitives for dealing with relaxed memory concurrency. You can define volatile variables and things like that. And then it has a rich system of what are called intrinsics, which are essentially kind of compiler extensions that aren't part of the language definition itself, but allow you to give well-defined calls to things like malloc for particular compilers. And then the nice thing about all this is that since this is a kind of common IR, they're able, the compiler infrastructure defines many transformations and analyses for alias analysis and various kinds of optimizations and so on in terms of these, this abstraction. And all in all, that makes LLVM a rather pleasant target for compiling high-level languages, so you can easily emit LLVM code and benefit from all of the optimizations that it's able to provide. Okay, so that's great, but it's a little bit complicated. And it has gotten more complicated over the years. So I started working on LLVM semantics back in LLVM version 2.6, which is way in the depths of history. And LLVM has been evolving over time. So these days, if you take a look at the LLVM reference manual, and I only had time for the table of contents, you'll sort of see that what started out as sort of a beautiful core language has kind of grown over the years. And many of these things are intrinsics that are there for special purpose domain-specific languages and so on. But many of these features were added over time to accommodate new kinds of program transformations and optimizations. And just to kind of give you a little glimpse of some of the, what I'll call semantic complexity of LLVM, I'll pick one example, which is about undef. So one interesting consequence of the fact that LLVM IR is this intermediate language, it's not a source language, it's not a target language. So it's intending to abstract over the details of many possible target architectures. So in some ways, it's providing a language that has much under specification in its behaviors. And in order to account, basically to allow for you to compile it to various different target platforms without committing to too much, too many specifics. And one aspect of that is something called undef, which is there in the LLVM. It's, in some ways, if you were to add this to a source language, you should think of this as a volatile register, or every time you mention it, it is a kind of arbitrary but undefined or indeterminate bit pattern. And undefs come in any type at all. So you can have an undefined 64-bit value, an undefined pointer, et cetera. And semantically, in the sort of description of undef, it's used for describing what happens if you read from an uninitialized piece of memory, or you load from volatile memory, or some of the operations are underspecified depending on the platform. Like, not all platforms treat bit shift operations in the same way, and so on. Okay, so undef is there, and they included, it's used internally to give the compiler flexibility when doing program optimizations. And just to kind of give you a little sense of some of the complexity of the semantics that this introduces, you might ask yourself, okay, what is the value of the variable y after you run the following little snippet of code? So here I'm saying that x is whatever you get for ORing the undef, which is a 8-bit integer in this case, so think of a byte, with the constant 1, and then taking y to be whatever you get by XORing x with itself. Okay? So any suggestions about what y should be after this operation? Yeah? False. Well, it should be 0. That might be one plausible answer. But actually, because of the undef semantics, you can actually choose many different possible values for y. And it's because of the kind of optimizations that LLVM would allow. So just to give you a sense of that, intuitively, since undef means an arbitrary but unspecified bit pattern, in this case 8 bits, we could think of the I8 undef as being some arbitrary element of the set 0 to 255, right? It's a byte. The constant 1 is just the constant 1. There's only one such value, so that's good. But this means if we were to sort of step through what happens when we evaluate x, well, we're taking x as undef or 1. So if you think about it, that's going to set the low bit of whatever value we happen to have to 1. So that means that x will be the set of all possible odd bytes, so 1, 3, 5, et cetera. And now if we were to XOR y with x, kind of point-wise, so we could arbitrarily choose any possible value for x and then do it again, well, 0 is an allowed value, and that is what most optimizations would lower the code to. But actually, according to LLVM semantics, you could pick any even number, because if you look at the set of odd numbers XORed with themselves, the only thing you know is that the last bit is going to be 0, and so you get any even value. Okay, so that's just an interesting quirk of the LLVM. And when we started formalizing this, I said to myself, that is crazy. Why in the world would x XOR itself not always give you 0? And you can go back and look on the LLVM developers list. There's a lot of discussion when they introduce this kind of semantics, and this is what is kind of there. But why does that make reasoning about LLVM code complicated? Well, consider these two things. So we have x multiplied by 2, which we just saw, depending on whether x is undef or not, could give you a set of possible values. And y, which is add x to itself twice, which again, semantically, should give you the set of possible values. So you might think that these are the same, right? Normally we think of multiplying by 2 as the same as adding to itself, but now with this undef semantics, if you go through the sort of set theory that I just showed you, well, it turns out that the y in the first case could be any even number for the same reason as we saw before, but the y in the second case, if x happens to be undef, well, it could end up being any number, because if you take 2 arbitrary bytes and add them, well, you can get any other arbitrary byte. So That means that since these two sets of values aren't the same, you can't just willy-nilly replace add by multiply by a constant for LLVM semantics. Although, of course, in the compiler, they do a lot of work to prove, for example, that X is not undef. And in that case, you could do this kind of optimization, right? And that would be important to get good performance because you might want to replace, multiplications by shifts, for example, and so on. Similar kinds of peephole things. So the upshot is, because of these weird semantics for undef, it's a little bit counterintuitive about what things might be allowed and what are not. So what's the problem? Well, if you look at that long list of features that I mentioned at the beginning, there are many of them, and undef is only one, sort of the tip of the iceberg in terms of LLVM semantics. There's another variant of undef called poison, which, if you're familiar with, is sort of an even stronger version of undef that if you touch it, it causes the program to become undefined. But even more subtly are things like pointer to integer casts and integer to pointer casts. So I mentioned that LLVM has a C-style type system, and C's type system is unsafe. You can always do these kind of bad casts, and yet you need to define what it means to do a correct optimization in the presence of all of these potentially unsafe features. So this means that it's a little bit hard to reason about LLVM code, and it leads to various kinds of compiler bugs and miscompilations and so on. And in fact, if you go back to the LLVM bug reports, I just found this one from 2017, so fairly last year. You can see it's due to undef. There's some problem with the simplifier, which is the kind of thing that rewrites as I'm showing. And if you look in the comments, he said, oh, I don't think that this is fixable under the current undef model, what it means to semantically model undef, unless we want to give up on other transformations. By the way, how did you find this bug to begin with? Well, if you look, there's a guy named John Reger who has been looking at LLVM correctness via his CSmith tool, and in this comment he mentions that there are many, many optimization failures. And so it turns out that even in modern LLVM, which has been well-tested, well-studied, you can get miscompilation of relatively simple programs, so the compiler will emit code that is incorrect based on interactions of features like this. And one way to see that is, so this study is a little bit old, but it's also performed by John Reger, who was in the comment on the previous slide. But I like this case study a lot because it kind of points out the potential failings of our compilers. So he has this CSmith tool, which very cleverly generates random test cases for C source programs, and then he feeds them to a bunch of compilers, GCC, LLVM, Intel's compiler, et cetera. And this is work from 2011 PLDI, and at the time, LLVM, of course, has changed a lot in the meanwhile. But at the time, he found 202 bugs in LLVM, 79 bugs in GCC, 25 of which were considered to be critical, and hundreds of bugs overall. And in fact, that comment that he mentioned was sort of the ongoing effort of applying the CSmith tool, even up to 2017, 2018. So this, finding bugs is good. And if you're curious about that line of work, I encourage you to go look at that and some other recent projects about something called Alive. But for the sake of my story, the upshot is that I think LLVM is a bit hard to trust, and well, any compiler is a bit hard to trust. We saw there are bugs in GCC as well. And if you wanted to use it for sort of mission-critical code, what can we do about that? Okay, and the approach we've been taking in our project about verifying the LLVM is formal verification. So the kind of work that John Reger's group is doing is great, and in fact, we should encourage that. But it only finds bugs. It doesn't give us new insight into how we should change the semantics of LLVM to, for example, make it easier to reason about or simplify, or to make sure that we've eliminated certain kinds of bugs. So that is our approach. And basically, the idea is we're going to build semantic models of the LLVM IR in Coq. How many of you are familiar with the Coq interactive theorem prover, just by a show of hands? Fewer than LLVM with a few hand waves. Okay, so I'm not going to assume too much knowledge of Coq, but just think of it as a very rich functional programming language. in which some of the programs you happen to write down are also proofs about the objects that you're defining in the language itself. And this is all part of a project that I'm involved in called the Deep Spec, or Deep Specifications project, where the verified LLVM is sort of just a little piece of this group of us that are all trying to apply this kind of interactive theorem prover methodology for various kinds of systems programming tasks. So I'm not going to mention all of them here, but for the purposes of this talk, some of the most related are the Certicos project at Yale, which is looking at verifying operating systems, and the Verified Software Toolchain at Princeton, which is looking at how to do C code. And so Vellum is a little bit of this. And what do we mean by deep specifications? Well, they're the kind of things you can write down in Coq. So they're very rich mathematical and formal specifications of complicated systems. They're two-sided in the sense that because the programming language IR like LLVM can be both a target of a compiler and the source of the backend code, you need to test it from both sides to make sure that the semantics is correct for both of those purposes. And the other key thing is we want it to be, these deep specifications to be live in the sense that what you're reasoning about is actual code that runs, not just a model of the code. And so this whole project has the goal of advancing sort of the reliability of safety of this kind of software. And one of the big inspirations for the Vellum project and this whole deep spec project is this ComCert compiler, which is done by Xavier Leroy at INRIA almost 10 years ago now, and where he did exactly this. So he built a fully verified C compiler in Coq, in the interactive theorem prover. And so that's sort of the archetypical example of one of these deep specifications. And the reason why I'm so encouraged by this line of work and why I think it's so fascinating is that very same C-SMITH paper where John Reger found all of these bugs in LLVM and GCC and so on also tried to do the same thing to ComCert, and they found no bugs. And this is one of my favorite quotes in any academic paper. I had to copy the whole thing. I'll let you read it, but I'll highlight a few of the salient bits. So this basically says that this formal verification works. So they said that the ComCert compiler is the only compiler that they tested for which C-SMITH cannot find any wrong code compilation errors. And they devoted 6 CPU years to the task of trying to generate random tests to break the compiler and weren't able to. And the conclusion they wrote about, this is not us, not in the Deep Spec project, and not Xavier Leroy, was that the apparent unbreakability of ComCert supports the strong argument that developing compiler optimizations in a proof framework where safety checks are explicit and machine checked has tangible benefits. Okay, so I think that's super cool. It's one of the really exciting things, and it's the motivation behind all of our work in Vellum. Okay, so we're trying to be a little bit less ambitious than ComCert because we're targeting at just the LLVM IR. There's enough complexity and semantics, as we saw with just undef, that we think that it's valuable to sort of take this core piece of the LLVM, build a Coq bubble around it, in which we can give formal semantics, create tools within that semantics for creating correctness proofs, use it to do things like extract interpreters that we can test against other implementations of the LLVM, and then use it for interesting program transformations, like in the case that you might want to enforce memory safety or maybe constant time algorithms. You could try to check semantically that those are enforced properly. So what is the Vellum framework? And I'll try to tell you as much as I can about it in the next 15 minutes. It's basically this idea that we're going to take this LLVM IR, we're going to wrap it in a little bit of OCaml bindings so we can interface with the existing LLVM pipeline, and then we're going to build on top of that in Coq this semantics so that we could build program transformations in Coq, automatically verify them, and then extract such program transformations in such a way that you can plug them into the existing LLVM pipeline. So you'll notice that this doesn't say guarantee no end-to-end compilation errors. Although if we applied it to every transformation in the pipeline, then that would be great. But for now, we're just aiming at a formal semantics for which we can do at least this. So how do we do that? Well, I mentioned already that SSA is a little bit like functional programming. So you have these sort of let definitions. And we know semantically a lot about functional programming. So what do we need to do in Coq? Well, we need to take that as our kind of core semantically, deal with all these kind of hard to deal with issues like undefined values and poison and so on, deal with effects like the complicated memory model that LLVM provides for doing structured loads and stores of the heap, and dealing with the concurrency and relaxed memory and so on. And so we've been making good strides about how to model semantically most of these features, and we're in the process of trying to figure out how to do this in such a way that we can do lots of good proofs about it modularly. And so the basic idea for our LLVM semantics is there's some kind of core thing that you can use to describe the behavior of an LLVM program. That's basically just defining the semantics of these control flow graphs that I mentioned at the beginning. And then on top of that, you can layer other kinds of behaviors, whether it's complicated memory interactions or undefined behavior, undef values, and so on. And then you can kind of grow this core language by adding things like external calls and concurrency and so on as you go. And so what this basically boils down to is, well, we're using Coq. It's a theorem prover. But it's also a functional programming language. And so we're writing, in some sense, an interpreter for LLVM in Coq. And to do that, we can use Coq's rich dependent type system. So I'm not going to go too much into the code, but these are snippets from the LLVM development. You can see, like any other programming language, Coq provides you a way of defining data structures like records that define the blocks of code that I mentioned, or the data structures that represent expressions and operations and instructions and so on. And this looks more or less like any kind of standard programming language. But Coq has some interesting limitations compared to most programming languages that you're used to. So in particular, because it's also a proof system, the code you write in Coq has to be a sort of pure, total functional language. Which means that it's very hard to write, well, you should not be able to write an infinite loop in Coq. And so semantically, we have to figure out how to write an interpretation function for LLVM code, which gives a meaning to Coq in such a way that we can reason about it. And if you think about it, of course, you can write an infinite loop in LLVM, so how do we reconcile these two things? How do we write an interpreter that doesn't go into an infinite loop? And I just want to kind of give you a little taste of this because it's not, I don't have enough time here, and it's also getting too down in the technical weeds. But the basic idea is Coq is a very rich functional programming language. We can define a data type that we can use to represent infinite computations. So even though we can't run an infinite computation, we can still represent it. And this data structure that I'm showing you here, called an interaction tree, is basically one way of doing that. And one important thing is that it sort of gives you a parameter to kind of say what effects this functional program could do, so it can have I/O effects and so on. And the other thing is that this represents infinite data. So just to kind of give you a picture, if we think of a computation as a tree, what could that mean? Well, it might go along doing some sort of internal steps that are not interesting from the outside world, like think of addition operations that are sort of internal to the computation. And then it might have an event, say a load from the external memory or an external function call, this sort of thing. That becomes visible as these, I'm showing them as green boxes. And then for each possible response to that event, we need to say how our code handles it. And so we'll end up with this sort of branching tree structure where each of these Ks says what is the continuation of the code in the case that, say, it returned an A. Maybe it goes on for a while and then returns the value 42, or maybe it goes on for a while and then does some other memory operation, and then those terminate in various ways. Maybe it fails by doing a division by 0 or something like that. Or maybe it goes into an infinite loop, never terminating semantically, but we can represent that infinite string of tals finitely and reason about it. Or maybe it keeps interacting with the rest of the world forever. And what we can do with that data structure is specialize it to LLVM. So this is, again, another bit of Coq code, but the important thing is you can see, it looks a little bit like the instructions that you might see in LLVM. So alloca, load, store. These are various LLVM primitives that we treat as interactions with the memory model. And this IO type says what the interface should be. And each of these little pieces of interface says what are the outputs to the environment and what are the inputs. So the long story short is, given such a complicated data type, or this data type, we can write an interpreter. And again, here's a piece of Coq code that shows you our sort of step function for this interpreter that takes a LLVM state and gives you back one of these traces, we call them, of interactions with the outside world as its return type. So this, if you're familiar with functional programming, is just sort of a monadic style interpreter where we've picked a particularly nice monad for representing computation. Okay, so the cool thing about this is you can then extract this interpreter and run it. So I'm going to quickly show you a demo of that. It's not a very exciting demo because it's just running a piece of code. But for example, if we take that factorial function that I had on the first slide, so here's the .ll file that contains that code. Well, when we extract the executable, we can take our Coq code, extract it to OCaml, compile it as an interpreter, and then run our interpreter on this particular thing, which you'll see it's calling factorial of 5, and we get 120, which is what you would expect. So cool, we can use this to write an LLVM interpreter, but we can do more, right? So what can we do with that? Well, we can find bugs in the existing LLVM interpreters by comparing them. We also need to know that what our semantics is agrees with other LLVM semantics, because that's a hard problem. We can use tools like QuickChick, which is an automated test generation facility to try to find bugs in our interpreter or LLVM semantics this way. And for the most important thing is we can try to use the semantics to validate program transformations by proving them correct in Coq. And eventually, maybe we could do a fully verified compiler. So again, I don't have a lot of time to go into what it is like to prove things in Coq, but here's a little example of a proof. I picked this one because it's small and it fits on the slide. It's not very interesting. It's just saying something about renaming the identifiers in your program. It says, if you consistently rename all the identifiers in an integer operation, then you could have done that before or after you've taken a step of computation. So it's kind of a fundamental renaming lemma. If the word alpha conversion means something to you, then this is a proof of that fact for a bit of our language. But the main point is that just like you can define functions in Coq, you can define lemmas. And you can interactively work with the Coq infrastructure to prove those lemmas about the program. And we've done that for many different kinds of optimizations. Softbound as what got us into this originally. We were looking at doing memory safety. Some of the interesting optimization passes of LLVM revolve around register promotion, which is called the mem-to-reg pass. And there are various analyses that you can prove correct with this kind of technique. So I want to just briefly sketch what that looks like at a high level, and I'm running out of time. But so for this mem-to-reg optimization pass, this is a register promotion pass in the compiler. It basically takes programs without SSA form, or sort of in a trivial SSA form, and introduces those phi nodes that I mentioned at the beginning. And that's very important for getting good performance because it enables register allocation and sort of many downstream optimizations. And just to give you a flavor of what it looks like, here's a little bit of C code. Here is sort of a little LLVM snippet that you'll notice uses some loads and stores to memory to model the C variable x, because that's what you would do. But an efficient version of this doesn't need to put x in memory. It can put it in a register. That's basically the optimization that's going on. And so mem to reg takes those loads and stores, et cetera, and removes them by introducing temporary registers in the appropriate places. And so this is a fairly complicated algorithm, and we're able to prove a variant of it correct by sort of breaking it down into a whole pipeline of optimizations. These acronyms here stand for things like dead store elimination, and they're sort of the fundamental building blocks for doing interesting optimizations of LLVM code. And the point is that with a little bit of work, we can express in Coq these aliasing properties. We can prove each of these little orange bubbles correct, for example, to use various lemmas about dead instruction elimination and so on, and then connect it all together to get a theorem that you can write down formally in Coq, but I've transliterated here as, this register allocation algorithm preserves the semantics of the source program. Okay? And then we can extract that implementation. So we had an implementation of this algorithm in Coq. We can extract it, plug it into the LLVM compiler, and run it against real C code, because it's just another LLVM pass like any other. And we can even then compare the result against the existing mem to reg. So by doing this, we don't lose any performance, because it's essentially the same algorithm. We've just verified it, and now we know that there are no bugs. And we're confident that this is correct. We can, there's interesting stories about differences between the sort of existing LLVM infrastructure and our version that I'm happy to take offline. Okay, so that's all great. What about some caveats? There's no free lunch, right? So verification of this kind is very labor intensive, and I would say we still don't have a good handle on dealing with verification at this scale. The performance of the resulting code, as we just saw in that little graph, might be the same, but the performance of the compiler itself, because we're building it in Coq and extracting it, is not as good as the C++ LLVM implementation, so that's a problem. And one issue with formalization of any kind is you're sort of pinned to a particular semantics, and the LLVM is a changing target. So what have we done about that? Well, for this first thing, I think there's a lot of progress being made in this DeepSpec project and elsewhere about how to do proof engineering. I haven't talked about automation and tactics and various libraries and so on that you can use to make all this more palatable. For performance, well, that's still an open challenge. I think you could use the unverified version of things if you want to just test and debug and then plug in the expensive compiler pass that you know is correct for the final release. Or there are other technical approaches like translation validation that try to get the best of both worlds. And for this LLVM moving target thing, well, this is one of the things we struggle with. They're adding features to LLVM all the time, and we can't really keep up. So what are we doing? Well, we've been re-engineering the Vellum project sort of from scratch, starting a couple of years ago as this DeepSpec project. And to do that, we've introduced a bunch of libraries that we hope can be useful in other contexts for doing with that. And we're experimenting with better automation to make all of this work better. Okay, so I just want to wrap up quickly by pointing you to, I mentioned already John Rager's work, but there's a lot of other work in the space of LLVM semantics, and I've had a lot of collaborations with some of the people on the slides, and you can take a look at other interesting projects in this area. Similarly, I mentioned CompCert, but there are also other tools like the Verified Software Toolchain. And if you're curious, for those of you who are still trying to, or potentially interested in getting into Coq itself, I recommend my colleague Benjamin Pierce's Software Foundations textbook, which is a free online introduction to Coq, and there are 4 volumes now that you can go up to interesting data structures. And once you've done those, you can take a look at Adam Shapala's Certified Programming with Dependent Types. And if you're interested more about DeepSpec or the Vellum project, you can find the Vellum development on our GitHub account, and it's also linked to from the broader deepspec.org web pages, where you can read about all these other fascinating projects that are applying Coq to systems code. So, thank you.